In this video, we're going to be discussing Lewis acids and bases. However, before we get to that, we're quickly going to recap Bronson-Lowry acids and bases. So Bronson-Lowry acids and bases, the acid acts as the proton or H plus generator, while the base acts as a proton acceptor. So you'll typically see the arbitrary, like the typical formula of HA plus your water, which gives you H3O plus and your A minus. So in this situation, the acid is the HA, base. H2O can act as an acid and a base. So that means your conjugate acid is going to be the H3O plus and your conjugate base. So it means that if the reverse reactions to occur, this would be the acid, that would be the base. And due to the fact that this reaction is reversible, it must be weak, as a strong acid would dissociate fully. And, conjugates only differ by an H plus. So that essentially recaps Bronson-Lowry acid and bases. So now we're going to be looking at Lewis acid and bases. So in Lewis acid and bases, it's better to think about it more generally as the formation of covalent bonds. So the acid acts as the electron, accepts electron density, while base donate electron density. So think about that with the donation and acceptance of H plus. It's a similar situation. So this is an example Lewis theory problem. So in this situation, I'm just going to draw some mechanism arrows. So these electrons in the chlorine would want to go to the aluminum, forming a bond. So both electrons in that bond are going to come from one atom. So this would form this structure. And then you would have a sigma bond. And then you would have a negative charge on the aluminum, formal charge, and a positive on the chlorine. And you can draw on all their lone pairs. And this guy would have there. This bond right here is known as a coordinate covalent bond, as both electrons came from one atom. So before we continue with more practice, we should quickly go over some good information. So in order for an acid to have a pKa value, it must be weak, as a strong acid would dissociate completely. Therefore, the pKa, the smaller the pKa value, the stronger the acid. So we know that pKa is equal to the negative log of Ka. And we know we can get the Ka from the concentration of the reactants over the concentration of the acid. And this gives us the Ka. And then you take the negative log of that to find your pKa value. So acids in their conjugate bases and bases in their conjugate acids have an inverse relationship, meaning that the stronger the acid, the weaker the conjugate base, or vice versa. So we're often being asked to decide which side of the reaction will be more favorable. So when you want to do that, you have to look for the stability of a base. So you're going to look at the charge, if there is one. If one has a charge, it is stronger, thus less stable. And then you want to look at the relative size of the charge-bearing atom if both have charges. Only relevant if in different periods. So the larger atom will be the weaker base, as it has more electrons to hold. Then you would look at electronegativity. So the more electronegative element will be the better and better able to hold the negative charge. So, however, if they're both the same atom, that wouldn't apply. Same type. Then you look at inductive effect. So this essentially electronegative atoms can electronegative atoms bound to the charge-bearing atom can withdraw electron density through the sigma bond. A sigma bond is one bond, while a pi bond is the second one, double bond. And that could help balance the negative charge. And then there's resonance. So if resonance structures can be drawn, means like if you have double bonds that their electrons can move around, a lower potential energy level can be reached, and thus it's more stable. So these are all stabilizing effects that would make it more stable. So let's take a look at some more practice problems, and then we'll decide the most favorable side. Alright, great. So in this example, which one would be the acid, which one would be the base? So we know since this has a negative charge, it's going to be the base, making the H2O an acid. So drawing resonance error, well, mechanism errors, we know the electrons are going to go from the carbon to this hydrogen because it wants to form a bond with it. And therefore, since hydrogen can only have one bond, the electrons in this bond are going to go to oxygen. So this would form CH4 plus an OH minus. And you have to have the conservation of charges. So I have the sum to the same amount, or they both be the same amount. So if we're to look at which side is more favorable, we have to compare the charge bearing atoms. So one is a carbon, while the other one is an oxygen. Oxygen is more electronegative, therefore it is favored as it's more electronegative and can better hold the charge. So this side would be favorable. Now let's look at this example. So again, we look at see if there's charges. Here, there's one, so this one would be a base. And this would be an acid. And also, if there's a positive charge, that would mean it's an acid most of the time. So now we look at mechanism. So we know that these electrons are going to go to this hydrogen, and therefore, same principle, these electrons have to go to the oxygen. So this would form something like this. And your H bound to the oxygen bound to a CH3 group. So this would have a negative charge, therefore this would be the conjugate base, and that the conjugate acid. So now looking at which side is going to be more favorable. So both the same element, both the same electronegativity. So now we look at resonance. So this, on the right side, in the products, there's a double bond in the molecule. Therefore, resonance can be drawn. Therefore, this side is favored. Alright, now we have some more examples. So we have a NH2 minus here. So we know this is going to be our base because it has the negative charge. And that means this has to be the acid. So what's going to happen with the electrons? Well, the electrons are going to try to go to the hydrogen, meaning that these electrons on that bond are going to have to go to the carbon. So this will form an NH3 minus, sorry, just NH3, plus the C triple bonded to the carbon, sigma bonded to the hydrogen. And this is going to have a negative charge because the carbon is 4, it's bonded to 5, has minus 5, negative 1. So now which side is favored? Well, we have to look at electronegativity for this one because there's no inductive effects, no resonance, nothing like that. So the carbon over here is less electronegative. That means it's going to be less stable. It means this side means the reactant side. This side is going to be favored. Alright, so now let's look at this example. So we have our base here, our acid here. And now what's going to happen? So the electrons on this oxygen are going to come around to this hydrogen, and electrons there are going to go to the oxygen. So this will form something like this. Negative charge plus something like this. And so this is going to be the conjugate base. This is the conjugate acid. And because resonance exists here, that means that this is going to have to be favored because it can go to a lower potential energy level. So this side. Okay, last example. So again, We're not exactly sure at first which one's the base and which one's the acid. But just to think about it, nitrogen or oxygen, which one is less electronegative? Nitrogen. So it's going to be, so oxygen's going to better hold onto its electrons, meaning nitrogen's going to be the one giving it up, making it the base. So now we have to draw our resonance arrows, our reaction arrows. So this is going to the electrons here are going to go to this hydrogen, and the electrons there are going to go to the oxygen, so that'll form an NH3CH3. That'll be plus, and an OCH3 minus. And while at first may appear confusing all the charges on this side, the fact that they equal out means that charges are conserved. So this side, the reactant side, will be favored just because since there's no charges, it's at a lower potential energy level. Alright, thank you for watching.